In this final example, we're taking a look at a physics problem. We want to calculate the force between 2-point electrical charges in empty space. The formula we're using is called Coulomb's law. Here are the variables. F subelectric is the electric force in newtons. The epsilon sub zero is the so-called permittivity of empty space. Q1 and Q2 are the two charges in coulombs, and R is the distance between them in meters. We begin, as before, by selecting a line, putting a space in front of it, coming up to Insert, and going to Equation. Again, as before, we'll select a larger font to make the equation editor easier to work with. Again, by typing in the Equation Tools menu the form for the E sub ELEC, which is an entity with a subscript, equal to something that's a fraction times something in parentheses and in parentheses we have something that's another fraction. On top we have something with a subscript followed by something else with a subscript, and on the bottom we have something squared. Moving right along, we start filling in these blanks. Capital F ELEC for electric is equal to 1 over 4. Make this a little bigger. Yeah, okay, that's better. 1 over 4 times pi times something with a subscript. And that something is the Greek letter epsilon and the subscript 0. Moving right along, on top we have a capital Q, subscript 1, another capital Q, subscript 2, divided by R squared. And that's the formula. On a new line, we can enter our quantities. We know that 1 over 4 pi epsilon sub 0 has a fixed value. It's 8.99 times 10 to the 9th Newton meters squared divided by coulombs squared. We'll enter that. 8.99. Now we're looking for a symbol that stands for multiplication. It does not look like an X. When we find that in our symbol set up here, times (10 to the 9th). Click the right arrow key to move over one, start entering again. And the units here, as we see, are in the form of a fraction, so we'll put in a fraction. We have n. It's commonplace to use a raised dot here. Where's the raised dot? The raised dot is right there. And Newton squared is an entity with a superscript. Meters, I should say, not newtons. Squared divided by the charge, which again is something with a superscript. It's capital C for coulombs squared. Now, we've done a lot of work so far, and this formula is going to be generally applicable for any solution of Coulomb's law in a vacuum. So we may want to save it and use it again. And to do that, we can click the arrow here, click on Save as New Equation. I will call it Coulomb's law, in vacuum, because it would be different in air or water or whatever, and we'll create a new category and we will call that physics. And the equation is now squared for future use, or rather stored but for future use rather. Moving along, we can enter our parenthetical variables. The first one is Q1, which is parentheses 3 times (10 to the minus 10th power coulombs). Q2 is, let's do it like this. Let's just copy this whole quantity right here, Control C, Control V, and enter the new numbers. This is minus 2 instead of 3, still 10 to the minus 10th coulombs, and we're done on top. On the bottom, we want to enter parentheses 2 times (10 to the minus 8 meter squared). Moving on to the next line, we multiply the entities in the numerator, get minus 6 times 10 to the minus 20th Coulomb squared. Now, for the sake of clarity, we'll put that outside the parentheses. On the bottom, we have 4 times 10 to the minus 16th meters squared. The important thing to note here is that meters squared cancels out top and bottom. Coulomb squared cancels out top and bottom. We're left with units of newtons, which gives us a warm feeling that our answer is correct, because the correct unit for force in metric units is the newton. Completing the math and shamelessly flaunting our detailed knowledge about how to handle exponents, we find the final answer is minus 1.35 times 10 to the 6th newtons, which is a lot of force, but although the charges is small, the distance between them is very small too, which accounts for the high result here. Another important thing to point out is the negative sign. The negative sign shows that the charges are attracting each other. In other words, the distance between them is tending to get smaller, which is what you would expect, because one charge is positive, the other one's negative, and everyone knows that unlikes attract. And that concludes that lesson.